Thank you. First, I want to thank the organizers for inviting me. It's a great pleasure to attend and give a talk in this amazing conference. So I'll be talking about bootstrapping NFO for superNMLs using integrability, but this is based on a paper that came out in 2022 and an upcoming paper with Simone Kernhood and Frank. Okay, now it works. So I don't think I need to motivate to this audience why studying NFO for superNMLs is interesting, but let me say a few words. So NFO for superNMLs is a great laboratory for studying strongly coupled quantum field theory. One might argue that NFO for superNML is one of the simplest theory that can study. So we can use it to learn about strongly coupled quantum field theory and apply it to more complicated quantum field theories that are of interest to us. So that's one main motivation to study this. Another motivation for me to study these theories is because of ADS-CFT duality. So we know through the duality that this theory is dual to type 2B string theory on ADS5 cross S5. So if we use conventional methods such as conformal bootstraps with relocalization or integrability to learn about this theory, we can apply these lessons to learn about dual string theory. So let me continue by saying some basics about NFO for superNMLs, just to set the ground. So NFO for superNMLs at conformal point is a maximally supersymmetric conformal field theory with gauge group as U and C. It has two parameters. One is the number of color and C. The other is the Young-Mills coupling, or packaged differently, TÜV coupling. And now these two parameters have dual string theory parameters, and they're dual to string tension and a string coupling, which is illustrated in the slides. I thought it would be nice to include like a graph of what the parameter space of this theory looks like. This graph is taken from this very nice overview of integrability in ADS-CFT from 2010. Interestingly, the status is still kind of the same. So here the x-axis is the TÜV coupling, the y-axis is 1 over the number of colors. When we have n going to infinity, we are in the planar regime. At very small TÜV coupling is where our gauge theory is weakly coupled, and we can do perturbative computation and go up the red line. At lambda goes to infinity, our dual string theory is weakly coupled. We have free classical strings, and we can add handles to our worksheet to go up in that direction. So that would be genus expansion. But in the middle, when it's white, it's very hard. It's attracting quantum string theory. We don't know much about it. However, in this talk, I'll just focus on this blue region planar limit and try to see the lessons we can learn in this regime. So the question I'm interested in is whether we can solve NFO for superNMLs in the planar limit at the conformal point in the modular space. What do I mean by solving NFO for? What I mean is finding all the correlation function of local operators. So in CFT, this would then reduce us to finding all the spectrum of local operators and their OPE coefficients. So if we know this, we know all the correlation functions. So that's basically what I want to see if we can get. The problem of getting the spectrum of single trace operator has been solved for more than 10 years now using integrability. So this part of the problem has been well understood and solved. But however, in the past 10 years or so, there has not been much progress in getting the OPE coefficient, and it remains a hard problem to get these OPE coefficients away from specific limits. Things like that. So this remains an open question, and this is precisely what I'm interested in answering today. So for this, we will introduce and use a tailored toolkit for determining this OPE coefficient by combining two of the methods that were previously used, conformal bootstrap and integrability. So that would be the goal of this talk, to get these OP coefficients. So let me tell you a little bit about the setup, which OP coefficients we are looking at, what's the object of our study. So as I said, we are interested in n-equal force-bearing mills in the planar limit. Just explicitly, this would be the limit that G Young mills goes to 0 and n goes to infinity with their product kept fixed. Now, in this limit, we look at the simplest half PPS operator that we can look at. That would be the stress tensor multiplet. It has a position space parameter X and arc charge parameter Y. Here, Y is a null vector on the parameterizing the S5 that makes sure OXY transform as a symmetric traceless tensor under the arc charge group. In our analysis, we will focus on multiple couplings. We'll start from the weak coupling and we go all the way to very strong coupling, 0.317. All right, so let me tell you a little bit about the correlator. So since the goal of this study is to use Bootstrap to find the OP coefficient, we will study the 4-point function to learn about the 3-point functions. So we're gonna study 4-point function of this half PPS operator, which we can use super conformal Ward identities to write as a free theory part plus a part that vanishes in the free theory. Here, Z and Z bar are just space-time cross ratios built out of Xi's, and alpha bar are arc cross ratios built out of Yi's. Now, the prefactor of HZZ bar, this Z minus alpha to the 4, comes from super-conformal Ward identities. It's just to impose that the correlator would be protected if Z is equal to alpha. Now, the interesting thing is that in the planar limit that you have NC to infinity, this reduced correlator becomes independent of NC, and it would effectively become like a correlator of 4 scalar primaries with only dependence on Z and Z bar. This is a desirable situation in terms of Bootstrap because we know very well how to bootstrap things that depend only on cross ratio, position space cross ratio. Just to mention one fact about this reduced correlator. This reduced correlator is dual to ADS Virasoro-Shapiro amplitude in ADS 5 plus S5, which has been the object of study recently and has gained so specifically see Tobias's talk later this week on this. Now, I want to just mention a few characteristics that this reduced correlator, because it's not a full correlator, it's a reduced correlator. I have to tell you that it actually has the characteristic that we want it to have for us to be able to bootstrap it. So the first thing that we need, and it actually has, is that it can be expanded. It admits an operator product expansion, basically. So the operator that show up in the operator product expansion of these correlator, you can see schematically they would be single trace operators or double trace operators. And then this correlator can be written as a sum over single trace and double trace operators. This is something we would need because what we wish to bound are these OP coefficients. We would need to have this expansion. We know, as I mentioned earlier, the spectrum, the delta and J of these single trace operators we know, but about their OPE, we don't know anything. About double traces, it's worse. We don't even know the spectrum. All right. So another nice property that this reduced correlator has is that it admits this OP expansion that we wrote earlier. You can write it, you can separate out the protected part from the unprotected part. So you can separate out the part that you know from what you don't know. This is just something that is technically useful. Secondly, it admits it's by itself crossing symmetric. So it admits crossing symmetry, which is again something very crucial for Bootstrap. Lastly, it's very well behaved in the Regel limit. It's actually better behaved than usual correlator in the Regel limit. So usual correlator, we know from bound on chaos, they go as this Z to, they're bounded from above, from bound of chaos, which says that they must go as Z to J star, where J star is bounded by 2. But these correlator, due to this factor of Z minus alpha to the 4 that I previously discussed, they go as, there are 4 factors more suppressed, basically. So they are they have enhanced behavior in the Regel limit. Now our question is, let's focus on this reduced correlator of first stress tensor. Can we use Bootstrap to bound the OP coefficient of the lightest unprotected single trace operator in the spectrum? So it would be in this sum, we would just focus on the lightest guy, the guy with the least scaling, with the smallest scaling dimension, basically. So just to get to set some context, I would like to mention what's already known about this Konishi operator that we would like to numerically get results on. So in the weak coupling regime, there has been perturbative calculation, and there are results for this operator up to 5 loops. Independently, this year in 2023, there has been result from Bootstrap and localization, but again, in the perturbative regime that matched with the 5 loop results. In the strong coupling regime, there has been studies of ADS for a Shapiro amplitude that fixes this, that gives an analytic expansion for this operator at a strong coupling. So these are the things that we know, but away from these 2 regimes, we don't really know much about this OPE coefficient. And the goal of this talk is to go beyond this regime and get results at finite coupling. All right. So let's see how our attempts of bootstrapping this correlator would go. So what is Bootstrap? Bootstrap is a method of imposing consistency constraints such as crossing, but now at the level of the OPE to bound the spectrum and OPE coefficient of operator that show up in the OPE coefficient. For example, consider the S and U channel crossing symmetry. If we can write it this way. We can just take one to the other side. And now we can OPE expand each of these correlators. Assuming that the same set of operators show up in this, both of these expansion, we get a sum rule where these f delta j are functions built out of the conformal blocks. Now we can think of this function f delta j as infinite dimensional vectors in the infinite dimensional vector space of functions of u and v. And what we can do is that we can consider a functional alpha such that when it acts on the operator that we would like to bound, here Konishi, it would give plus or minus 1. For any other operator in the OPE, we would just get something positive. That's the only restriction we want. And then this would give, this would help us to rewrite our sum rule in this specific way. We just keep every terms except Konishi operator and the things that we know from the protected part on one side and keep the other 2 on the other side. Here, because this is positive, if lambda squared was also positive, we would get the right-hand side to be positive, and then this means that we can get, depending on the sign of Konishi, we can get either lower bound or upper bound on the OPE coefficient. But then it's crucial for this argument that this OPE coefficient is positive. However, this does not work here because double traces do not enter with positive coefficient in this sum. So this, you might think it violates unitarity, but it does not, because leading order OPE coefficient of double traces already enter the correlator at the free theory level. So the thing that enters in this reduced correlator are the correction to this OPE coefficient, which we don't have any positivity on. So this naive approach of Bootstrap does not work here. And the only way to go forward would be if we had a way to remove these double traces. So we would like to eliminate these double traces. The question is whether we can, and indeed the answer is we can. So in the following, we will going to show that indeed we can remove these double traces. We're going to build some rules similar to what I've shown you, but now it's going to be in terms of OPE that only is sensitive to single trace operators. And then single trace operators enter the OPE with positive coefficient. Their scaling dimension we know from integrability. So it's all very good and understood. Now, what we can do after that is that we're going to get the spectrum of single trace operator from integrability. And then, right. This would tell us where to impose positivity, because we had to impose positivity on all the other operators in the sum. This would tell us where to input positivity. That's where the integrability comes in. And then what we can use, what we can do is that use these sum rules and the places to put positivity, all these construction inside numerical bootstrap to get bounds on the OPU coefficient. Okay, this is going to be the outline of the things we need to do to get the results. I'm not going to bore you with all the details of how to do this. I'm going to tell you a little bit about the logic of how you get these sum rules, and at the end, and after that, I'm just going to show you the results that we get, right? Okay, so let me tell you how the double traces are actually killed. And what's the menu of sum rules that we are allowed to use. So what we need to do, as I said, is to decouple the double traces from the sum. We can do this by defining what's called the double discontinuity of the correlator. This is something familiar to this audience because it's close to imaginary part of the amplitude. But here the difference is you take the correlator in the Euclidean regime and you subtract the analytic continuation above the cut and the analytic continuation below the cut from the Euclidean correlator. This is a little bit different from imaginary part, but it's similar. Now, the important thing is that this double discontinuity, when you act with it on the block, it kills the double traces. How it does it is that when it acts on a conformal block, it multiplies it by sine squared with this prefactor. And for double trace operators, this prefactor is specifically proportional to 1 over n. So this sine squared makes the double trace operator suppress as 1 over nc squared. And this would effectively decouple these operators in the planar limit and would just take them to the next order in 1 over n. It would make them a non-planar contribution. All right, so we showed that this double discontinuity, the double discontinuity would kill the double traces, but there's a problem. This double discontinuity picks a channel similar to imaginary part of the amplitude. You can choose which branch cut you take the discontinuity around. So it's not crossing symmetry. But what we can do is that we can use this double discontinuity, again, in the same logic that we use the imaginary part inside the dispersion relation to get back the crossing symmetry correlator. Now, the problem is whether we can find such a kernel that does this job for us. And indeed, yes, we can find such a kernel that was done before. And then what we do is that after finding this dispersion relation, we would OP expand the reduced correlator, this H, inside the double discontinuity. Now this OP expansion inside the double discontinuity would just have the single trace operator and the protected part. And then by defining the dispersive transform of each of the block, each of the constituents that show up in the previous expansion. So by defining this to be Polyakov-Regge blocks, so we give it a name. It's in many ways similar to the usual blocks, but it's different. It's defined as this. In addition, by noticing that at the very, very strong coupling, all non-protected single trace operators become heavy and decouple, we argue that the double discontinuity of the protected correlator should be the same as the double discontinuity of the strong correlator. By using these two facts, we arrive at an alternative expansion of the reduced correlator. Here we have H strong, which is a function that we know, plus a sum that's only over single trace operator. But note that here, instead of the usual conformal block, we have what's called Polyakov-Regge blocks. Right. Now, this would be the key formula in our analysis. We now use this expansion of the correlator to obtain various sum rules, such as what we did before in terms of the usual conformal block. We can repeat everything, but now in terms of this Polyakov-Regge blocks. and we can get some rules that are only sensitive to single trace operator. So this would be the crucial thing. It's just that we could write the OPE in a way that's only sensitive to single trace operator. All right, so I'm just gonna mention briefly what type of sum rules we can get out of this. So the type of sum rules that we can get can be categorized as follows. So there are some sum rules that impose crossing symmetry, similar to what we saw in the beginning part of the talk. It would just imposes crossing symmetry, that the correlator should be crossing symmetry at the level of OPE. We can do that both in position space and in Mellon space. Another type of sum rule that we can get here that we didn't have before is that because the kernels of the dispersion relation are not unique, we can have different kernels, and we can impose at the level of OPE again that these kernels should give the same result. And this would give a non-trivial constraint for the OPE data. All right. Another type of sum rules that we can include are sum rules that impose integrated constraint. So this would relate certain integration of the correlator to the known functions of the coupling. Since the first two types of the sum rules that I mentioned are kind of self-explanatory, I'm going to tell you a little bit about the third type, which is of crucial importance as well. So integrated sum rules are sum rules that relate the integrated stress tensor correlator to the derivative of the free energy of the mass deformed theory placed on a sphere. So it would be a certain type of derivative. It would be for derivative with respect to mass, or two derivative with respect to mass, or two derivative with respect to coupling. Now the point is that the free energy can be calculated from supersymmetry localization. We know what that is. So basically what this sum rule do is that it's like if you integrate the correlator, then you get some function of the coupling that you know, and this again, if you OPE expand this correlator inside this integration, you get a non-trivial sum rule that you can apply. So it tells you more information about what coupling that you're at. All right. So now, as I promised, I will give you the result. And don't bore you with the details of numerical bootstrap. So using these sum rules and applying numerical bootstrap, we can get for the first time rigorous bounds on the OPE coefficient of Konishi that interpolates nicely between weak and strong coupling. So you probably see two black hairs here that interpolate from weak and strong coupling. That's our numerical result. You probably don't see here, but there's a blue line that's the weak coupling result, and then there's a red one that's inside this window of upper bound and lower bound, and you see that it kind of blows up here. So to see how it blows up and how the analytic predictions are close to the actual rigorous bounds that we get, let's just zoom in a little bit. So you see that you see for the actual curve, it interpolates nicely between the strong and weak coupling, and where it blows up, it's very nice and smooth, of course. The strong coupling expansion is becoming valid above 0.8. You see below 0.8, it's actually outside the window. So it's kind of the strong coupling expansion does not work below 0.8, but it remains close and completely blows up here. The weak coupling expansion remains valid up until here, but it blows up again at 0.25. All right, so this blue curve that I showed is the state of the art at small coupling, and is within the rigorous numerical window for G equals 0.5. So the weak coupling expansion works for G less than 0.5. The red curve is from the analysis by this group of people, and I'm sure you're gonna hear more about it later this week. It works for G bigger than 0.75, as I mentioned, but it remains closed up to G 0.25, which is, I mean, it's an interesting fact. It shows that this expansion works quite well. For G equals 0.1, okay, the highest loop result is this. Actually, the 6 loop error is the size of the window. So we might hope that with this numerical analysis, we can even predict higher loops and then make guesses of what higher loop can be and do things like that. Now, I also want to mention that these lower bounds that we get, they were only possible once we included the integrated constraints. So integrated constraints are super important in our analysis. Okay. Here, I would like to mention that the strong coupling regime is very, very simple. A strong coupling regime is captured by flat space. It's the limit that you send RADS squared over alpha to infinity with S to U to infinity with this combination fixed. Now, the point is leading order OP, when G is very, very large, is captured by flat space. We can also see this numerically. We see numerically that our, we can see it numerically as well, but at the analytic level, we can also see that the sum rules that we use become the same as flat space dispersive sum rules that are used by many people in this audience up to a normalization when you took very large G. So it's really, so the sum rules are the same. And also at the level of the numerical bootstrap, you can see that the bounds you get are also the same. Okay, so with this, I arrive at the summary. So for the first time, we find rigorous sandwiching lower bounds and upper bounds for the OP coefficient of the Konishi, which interpolates nicely between weak coupling and strong coupling. By comparing it with strong coupling and weak coupling in analytics, we can see exactly where the results break down, where the analytics break down. Now, expanding ADS for Zahra-Shapiro amplitude around flat space correctly predicts OPE down to 0.5. Maybe since it remains so close, maybe by pushing the curvature correction, we can actually go to 0.25. This is a question for Tobias. Whether this can be done in short time or not. And then I also mentioned that a very strong coupling and numerical bootstrap analysis become the same as flat space problem. Okay, we in the same way, we can also bound other operators. Yeah, the story remains the same for other operators in the OP expansion. All right, so I'll just put the next steps. An obvious important question is whether we can fix ADS via Zahra-Shapiro amplitude at finite Tupft coupling using this data. That's an obvious next step. Then there is the question of, can we go beyond linear optimization? Then we can also think about higher KK modes, applying this to higher KK modes, applying it to other theories, which you have integrability data like ABJM. So yeah, these are all the questions you can ask. And with this, I conclude.
Thanks very much. We can take a couple of questions. Do you have any expectation of this analytic function? What is, do you have any, maybe a sign or something else, or polynomial or something?
For the analytic function that we show, yes. So it's actually, okay, like you mean guessing what it can be?
Yeah.
Yeah, so we did try playing that game, and guessing works. Let me show you the plot. Guessing works well to some regime. You can put some, like with some hypergeometric function, you can get actually like a little bit closer, but yeah. So you can get, you can do some guesses for like what the higher order correction would be.
Okay, thank you.
I mean, maybe just a similarity. You could do some conformal Pade approximation that takes into account where the singularities are in the imaginary coupling. And did you try to plot that against your rigorous bounds? Because
For
on
the-
this plot, it's hard to see how
Okay.
thick the rigorous bounds are because they're so narrow.
Yeah, it's the window is very narrow. I mean, that's a niceness of it, right? That's the fact that you're upper bound and or you mean the fact that it's not zoomed in.
Well, I'm asking if that thickness is the thickness of the line you chose to print it with, or it's actually the thickness of the error bars on the.
So the error bar, you can see there is some gray region here, but that's the error bar. And you see that the error bar is
Okay.
becoming smaller and
At
smaller.
larger, I guess you can see
Yeah,
it too.
yeah.
Okay. Anyway, it'd be interesting to compare this with some kind of conformal pade
Yes,
approximation.
absolutely. To get this curve analytics, yeah.
All right, let's thank Zahra again.